Меня зовут Volker, я работаю в SAP или SAP в Германию. Наш отдел делает SAP JVM, Java виртуальная машина, которая базирована на HotSpot. Но мы сделали порт на разные CPU, как Itanium, PowerPC, Z-Architecture и на другие операционные системы, IX, HPUX. Да, я тоже committee reviewer в OpenJDK и project lead от PowerPC Exporting Project в OpenJDK, где тоже SAP сейчас много сделает. Вот, к сожалению, доклад был заказан по-английски, поэтому сейчас перейдем на английском языке. Но если у вас вопросы есть, пожалуйста, я весь день буду здесь, и завтра спросите, не волнуйтесь. Okay, so let's begin with the question. Who of you have already built the OpenJDK from sources? So, quite some people. So this is just the introductory slide. So nowadays it's really very easy to build OpenJDK from source, and I would advise everybody who is interested in hotspot or virtual machine technology to do it. It's just really a few steps. You just clone it, then you go into the directory. So actually the OpenJDK, it's not one repository, but it's a forest of several repositories. That's why you have to call a script called getSource, which will clone all the nested repositories like Hotspot, LangTools, JDK, and all the various stuffs which are in there. And now with the new configure-based systems, configure-based build system, which was introduced in Java 8, it's really easy. You just call configure, and usually on Linux you don't have to give any arguments. On Windows it's also got quite easy now. You just need Cygwin or MinGV installed. You need a compiler, Visual Studio compiler, or even the SDK. It's enough, the Microsoft Windows SDK. And you need the free type sources. That's all. On Linux, actually, usually all the dependencies are already installed. And then when you build an OpenJDK yourself, usually you want to build a debug version of the OpenJDK, because the debug version, it's not only easier to debug because it contains the debug information, but it also, the hotspot is instrumented with a lot of debugging, tracing code, which helps you a lot. So I don't know if you know it, but you can give the hotspot 1,300 options, like it's this -XX options, and it's 1,300 if you build the debug version. So to build the debug version, you just say with debug level slow debug, and when you build the debug version, the debug info is packed into a separate file, and if you don't want to unzip that by hand, you can also say disable zip debug info, but that's just minor issue. So then you type make images, log equals debug is to see more of the build process, but it's not necessary. And even on my small laptop with like 2 cores, it builds in about 8 minutes. So if you have a decent machine under your desktop, it will build in 2 or 3 minutes. So that's really fast now. And then you have your own version, a debug version of the VM, and you can try all these fancy options, like say unlock experimental VM options, print flags. Print flags will print you all these 1,300 flags. There is a command called print flags with comments, which will give you some explanation for some flags. Some are not very explanatory, but you'll find out what it means. And there are 2 other interesting options, like print flags initial and print flags final. So print flags initial gives you the initial setting of all the flags. And then during VM startup, the hotspot is checking like how many CPUs to have, how many memory, and it's this thing called ergonomics. It tries to set up some parameters so that your VM runs best on your current system. And then print flags final will show you the actual settings which you're running. So now let's get to the code. We start with a very easy, simple hello world program. On the left side you see the Java code. On the right side you see the bytecode, which you can look at with the Java P command. So you see hello world program contains like 8 bytecodes. That's not too much. And Now let's try one of the new options which is available in the debug version of the VM. It's called count bytecodes. If you run Java with -XX count bytecodes, the VM prints out how many bytecodes it has actually executed, and you see it's more than 3 million. So for our 8 bytecode long hello world program, the VM needs about 3 million bytecodes. That's quite a lot, and it increased quite during the last years. When I first did this talk about 2 or 3 years ago, still with Java 7, the first versions, it was just about 1 million, then it got 2 million, now 3 million. But just recently, the last version which I built yesterday when I prepared the talk, I saw that it's decreased again to about 1 million. So with the new modularity project in Java 9, I think not so much things get initialized anymore, so the amount of bytecodes which get executed during VM initialization is hopefully going down again. So let's look at other interesting options. We have, for example, print bytecode histogram, so you can see how many % of each bytecode, which bytecodes are the most frequent bytecodes. So for example, fast iload or integer load 1, it's one of the most frequent bytecodes. You can use this information if you write your own interpreter, for example, or own compiler to know which bytecodes you want to optimize. And the last option I want to show on this slide is trace bytecodes, which is very interesting because it prints you out every bytecode it gets executed. So when you start the hello world program, you see the first bytecode which gets executed. It's from the static initializer of object class, which is natural because object has to be initialized first. On the left side, you see the thread ID, and that's the absolute number of bytecodes, so the first, second, third, and the third column contains the bytecode index in the respective method. Okay, some words to the interpreter. The VM first starts in interpreted mode. So before the JIT compiler can kick in, the HotSpot VM runs the bytecodes in interpreted mode and does profiling. So to gather some profiling information such that the compiler later on knows how to optimize your code. Actually, the HotSpot contains 2 different interpreters. It's the template interpreter, about which we will speak now, and there's also a so-called C++ interpreter, which is not used so frequently. And but if you want to port a HotSpot to a new architecture, you probably can start with C++ interpreter because it doesn't contain so much machine code. So here's a small example of how the template interpreter works. You see this here, it's the bytecode stream, it's just our bytecodes from the class file which are in memory. And you have a bytecode pointer, which is usually a register which is reserved for the bytecode pointer, so it's fast. And this bytecode pointer is just an index in the template table. The template table is just a C++ array. You know there are 255 bytecodes. So there's a table of 255 entries. And with each bytecode, you can address into this table and get the address of some code snippet, which lays in the code cache, and which contains the code which implements this bytecode. So for the integer add bytecode, we get some code which is similar to the one I showed here. So you see, we just move the top of the stack into the DX register. We increase the stack pointer, then we add the X register to the AX register, which contains already the second parameter of the integer add parameters. And then R13, register R13 is the bytecode pointer from above. So now we load the bytecode pointer +1 to the BX register, increment the bytecode pointer, so it points to the next bytecode. Then we move this address, this is actually the address of the template table. We move the address of the template table into another register, and then we jump to the next bytecode, because BX, it's the register which contains the next bytecode, and R10 is our template table address, so that's like an array dereferentiation. And we jump to the next bytecode and execute. And in this way, the template interpreter is working up all your bytecodes. Okay, now let's show this in reality. I have prepared some examples here. So let's first run with the command print interpreter. There is a command called xx print interpreter. And you can see this command, when the VM starts up, it first has to generate these code snippets, which I have showed you before. And you see, it's actually more than 255, it's 262. That's because the HotSpot also generates some helper snippets, like this one, for example. It's a signature handler, because the HotSpot VM, for example, has to do calls from Java code, from interpreted Java code to native code when you do a native JNI call, for example. And the native calling convention and the Java calling conventions, they are different. For example, the register passing the argument passing in registers or memory is different from the interpreted Java frames, the compiled Java frames, and the native C frames. And so there are like small code snippets, like a signature handler, which takes the arguments on the stack, which are in Java calling convention, and converts them to native calling conventions. That's why we have more codelets than 255. But if you are looking for our integer add bytecode, you see it's actually exactly the code I showed you before. We load one parameter into AAX, we load another parameter into the DX register, we do the actual add instruction. Then we increment the bytecode pointer and we jump to the next bytecode. So this is how the interpreter works. Okay, now let's jump into a GDB. Let's debug Java now with a native debugger. What we first do is we run again this command to grab the address of the bytecode and to place a breakpoint into generated code snippet for iadd. So I say again run -xx print inter print interpreter hello world, and we grab for iadd. Yeah, I forgot to say that I have used the underscore Java options environment variable. Don't know if you're aware of this, but with the Java options environment variable, you can specify options which are loaded by the JVM on startup. So these are, I've turned on special things like tiered compilation, on-stack replacement, compressed oops, because this will make the examples more harder to explain. But actually all the examples would work even without these options. So the important point is now that we know that our iadd bytecode gets generated to this address when the VM starts. And we can now place a breakpoint here and hope to stop at the first iadd bytecode. Yeah, there was one thing I forgot to show you. I didn't show you the trace bytecode options. And I wanted to do this before we go into the debugger, because there's some information which we need later on. So we say trace plus trace bytecode hello world. So as before on the slide, you see the static initializer of object. It's called first, but you are interested in the first occurrence of the integer add bytecode, and you see it's bytecode 116. The 116th bytecode is the first iadd which gets executed, and it's in the method thread group add. Just remember that for a later example. So I go back to GDB, and yeah, I just placed the breakpoint at this address, which is where our iadd bytecode was generated at. And now I run the program again and hope that we will stop there. So you see this is the first problem. The GDB says it cannot place this breakpoint at this address. And that's natural, because when GDB starts your Java virtual machine, this address isn't used. It's not even mapped. Because only during VM startup, the VM allocates some memory, native memory, and places the generated bytecode there, and only after the interpreter is generated, we can place the breakpoint there. So what can we do? First, we disable our breakpoint. We place another breakpoint into a method called init globals. So this is just an internal method of the hotspot, and which does initialization of the whole virtual machine. So let's run this one again. Takes too long. Okay, so now we get in the init globals method. We just finished the method, so we step out of the method, and now we can enable our breakpoint again. So now the breakpoint is set. You see it's enabled and it's set, because at this point in time, at this address, there is already code, the code for the integer add. And if we continue, we will stop at the breakpoint. And this is actually the first time the codelet for integer addition is called. And we want to know where we are. We hope we are in the thread group add method. But of course, GDB has no idea where we are, because we are now not in a native C frame, but we're in generated code. So there is no debugging information available, and the frame layout is different, like from C frame. So GDB has no idea what to do. So helpfully, the hotspot contains some helper functions. We can, for example, call the help method in, and that's actually a function implemented in a hotspot, which is only available in the debug version, and it just contains little helper functions which can be called right from the debugger to give you some information about the internal state of the virtual machine. And we will use now the print native stack command. So it's called PNS, and we have to give him the current stack pointer register, the frame pointer, the base pointer, how it's called, and the PC. And when we call that, we now get a mixed stack trace. You may know this from HS error file. I think most of you know HS error files. Yeah, if the VM crashes, you get the file, and it has something like called a mixed stack trace. So all the frames starting with a lowercase j are interpreted Java methods. So you see, we are unfortunately not in thread group add. We are another method. It's called Java NIO heap byte buffer. We will see in a minute why we are not at that in thread group add. But you see, the stack trace contains interpreted frames. It contains lowercase v denotes C frames, native C frames from the hotspot itself, from libjvmso. And it also contains just the usual C frame. So it's from libpthread, it's the start thread. That's, well, for sure the first method. Then Java main, it's the launcher from a Java executable. And JNI create Java VM. You probably know this method. It's the starting point of the VM. You also call this when you call Java from your own launcher. And then you have some VM calls, and finally, at this point, it's call stub. This is also generated code, and this is the first Java method which is called. You see it with a small j, so it's interpreted Java method. Okay, so let's look at the assembly at the PC where we are, because we expect it to be in thread group add. As you can see, this is actually the right bytecode. It's the same assembly for the add bytecode. But for some reason, we are not the place we want. So let's analyze this address. I told you before that this should be the template table. So we print info. Let's see what GDB thinks about this address. And indeed, GDB tells us that at this address there is an object of type template interpreter active table. So this is actually really the template table which I showed you on my slide here. That's actually a C++ object which contains the addresses to the generated bytecodes. So GDB knows this object. It just doesn't know the code, the generated code. So we can, with ptype, we can have a look at the type of this template table. Template interpreter.
Could you please move console to top?
Excuse me?
Could you please move console to top?
Move the text up.
You mean the text or?
Hit enter several times. Hit enter.
Okay.
Oh, that's sorry, that repeats.
Yeah. It's difficult because usually type on the back line of your console. So, yeah, but you see it 2 times now. So the type of the template of the template table, it's not actually just a simple array with 256 entries. It's actually 9 different tables with 256 pointers to code. And that's because of an optimization which is done by HotSpot, and it's called top of stack. So as you know, the virtual machine is a stack machine, and to optimize this, the HotSpot caches the top of stack value in a register, so it doesn't have to load it and store it every time to the stack. And different bytecodes have different behavior, and some bytecodes, they leave their result already in the top of stack register, which is the AX register, and some more complicated bytecodes, or for example floating point bytecodes, they don't compute the result in AAX, so they just push it on the real hardware stack. And depending on the top of stack state of a bytecode, the codelet has different entries. So there are bytecodes. The IAdd can be called with the first argument in RIX, or it can be called with the first argument already still on the stack. Then it has to push it into RIX itself. So to illustrate this, I will print now the entry of the different tables. So let's cast it to void pointers. So we want from template interpreter active table. So we take the table object, and there are constants defined in the HotSpot. So ITOS means integer is top of stack. It means that ITOS means the top of stack register contains an integer result. And so we take this table and we take it for the bytecode IAdd.
And you just know that the ITOS variable name?
Yeah, I just know it. I mean, you would have to look it up in source code first. Okay. But there is an enum which defines, there's also an enum with the bytecode IAdd, which I have just typed, so you would have to know that, yes. Ah, yeah, sorry. Yeah, you're an expert. Yeah, good.
Sorry for interrupting.
No problem. And you see, for bytecodes which place their result in the top of stack register, the entry for the IAdd will be this address, and for bytecodes which don't place the result. VTOS means void, so it means top of stack register is void, it doesn't contain a value. You see, it's actually this address. And if you print now this address, you can see that it's actually our IAdd bytecode, but this entry point, it's actually at this address here. It first loads the first argument from the stack into the AIX register and increments the stack. And the second entry point is this one. It already assumes that AIX contains the actual value. So, and what we've done is we've placed our breakpoint at this place. So that's why we stopped. We didn't stop at the first occurrence of IAdd, because the first occurrence of IAdd, we will see. We will place now the second breakpoint at the second entry of the address. Okay, we now have to disable them and restart the program. So I restart my program. We will now first stop in init globals first, and only after the bytecodes have been generated, we can enable our breakpoints. So you see, we now have stopped in the third breakpoint, the one which is the second entry into the IAdd. And when we call our print native stack trace function, we are actually really in a thread group add. So it depends which bytecode comes before the integer add, how it calls the next bytecode. And every bytecode knows what it does. So it has the different bytecodes have different addresses for so the codelets for the different bytecodes have different values here for the template table entries. So that's actually how the template interpreter works. One more small example. Debugging like this, the interpreter, it's quite hard. You may want to stop at a specific breakpoint, for example. So there is a command for that. It's called run -xx stop interpreter add, and you just give him a number. 116 should be our first IAdd bytecode, and then hello world. We start from the beginning. We have to disable our breakpoints and continue. Yeah, but actually the program runs. We also disable this breakpoint. We don't need it anymore. But it runs and it doesn't stop. So in order to really stop, we have to set another breakpoint into another helper function in the hotspot, and it's called breakpoint. So very easy to remember. So I now set a breakpoint in the breakpoint function, and run once again with stop interpreter add. And hopefully we will now stop in our breakpoint function. Yeah, we stopped. And when we look where we are, then again you see that the GDB knows we're in the breakpoint function. But below the breakpoint function, it doesn't know what there's below, because it's again generated code. So this feature, stop interpreted add, it works like this: that every bytecode contains the hotspot maintains a bytecode pointer, and every codelet does a comparison of the actual counter and with the value where we want to stop. And when we reached that bytecode, it just calls this breakpoint function. So that's why we had to set this breakpoint. That's actually like a callback. So we tell the VM we want to stop there, and then it calls this helper function, and we can set a breakpoint there if we want. If we don't want, it just runs through. We can call our print native stack trace function, and you see in the mixed stack trace, you see that the actual Java frame, thread group add, where the first I-add occurred, it just calls the OS breakpoint function, and that calls the C function breakpoint where we set the breakpoint into. We can call another helper function which is very useful. It's called just find, and you can give him a arbitrary address, and it will look in all the hotspot data which is available to see if it can make sense of this address. So it scans the heap, the code cache, or the internal data structure. So when we say call find PC, PC is the actual program counter. It says us that the current PC, it's an offset into the libjvm. That's because we are currently in the breakpoint function, which is a C function. So we have to step up 2 times in the frame and call this function again. We are now again in the generated code, and then you see that the hotspot actually knows that we're in generated code, and this code belongs to the integer add function. And just as a last example for the template interpreter, we just print now the disassembly of the I-add function again. You might think we've done that enough before, but you will see that the current bytecode for I-add is quite different, and that's because the hotspot has now generated code which does exactly what I told you before. So it loads this global counter value and increments it, and it compares the this is the compare operation. So it's 74 hex, and if we print 74 hex, you will see that it's actually 116. So here it compares the global counter value with 116, and if yes, it just calls our breakpoint function. So this is how it works. This code is only generated when we use this function. If you don't use this function, the code isn't generated. It's the same with debugging. If you enable debugging, Java debugging, or if you enable JVMTI, every bytecode will contain some instrumentation code. If it's not enabled, you don't need this code. Okay, so that's all for the interpreter so far. I will switch to the next example, which is for the JIT compiler. So you probably know that interpretation is only the first step. After methods run hot, it means after they get executed 100, 1,000 times, the VM decides that it's now time to compile it to native code, so it gets executed faster. Previously, there were two compilers, the C1 client and the C2 server compiler. C1 ran faster, C2 generated better code. You may remember that there were client VMs or server VMs. You could choose with the -client, -server option which JIT compiler to use. So for Java 8, now you have both compilers by default in the hotspot, and they use a so-called tiered compilation system. So it means after the VM decides to compile a method, it first compiles it with the C1 compiler, which runs pretty fast, but still generates code which does profiling. And if the C1 compiled method is called another 100 or 1,000 times, which is all configurable, it then finally decides to compile it on the highest compilation level, C2, and then the C2 compiled code doesn't contain any more profiling information and should run at the best speed. So I have prepared a small example here, which is actually, it was a real bug in one of the first releases of JDK 8. It was found by Alexei Shipilov, which is around here as well, and he fixed it, fortunately. And but this example will demonstrate this problem and how it's possible to find such a problem in the hotspot VM itself. So the program is actually pretty simple. So our main method just calls in a loop an update function. And the update function does nothing else than incrementing a long variable, a static local. We have a long field and an atomic long field. And both are incremented by constant. We have defined a final constant here. It's something like 4 billion. And we increment the long as well, like the atomic long. And after we've incremented both, we compare their value. And I think everybody agrees they should always be the same. But for any case, we added an else branch to print an error. And these functions are just here so that we don't print OK or error every time we run through the loop. But once we are OK, we print OK one time, and then we stay like with one OK. When we go to error state, we will print one time error and reset the values and run further. OK, so let's run this program. So it's called atomic long integer. And let's run it 10,000 times. And, ooh, atomic long. Let's try the other window. Maybe I haven't set the class path. Sorry for that. Java atomic long integer 10,000. Ah, it's called atomic long test, sorry. My fault. Yeah, it's actually a test program. Okay, so you see from the first iteration, the values are equal until the 10,000 iterations, so no problem. So now we run it 10,000 one time, and you see, boom, 10,000 first iteration, we get an error. The values are not equal anymore. So let's do it like 10,000 two times. So it's OK again. So just the 10,000 first iteration failed, and then it's OK again. So let's run it 20,000 times. So again an error, 20,000 iteration. So if you run it 20,000 6 times, it's still an error. So it seems it 200,000 times, 200,000 times, it just stays in error state. So strange, yes? Shouldn't be like that. So let's debug it. Let's debug it. So usually Java developers take a Java debugger, right? So usually you take Eclipse, but it would be too complex here on this small screen, so I just take GDB. It's enough for our example. Launch atomic long, mistype, sorry. Atomic long test 20,000. And we set a breakpoint in the branch where we print an error. Stop at atomic long test line 17. And then we say continue. So in the debugger it runs no error. So it doesn't help very much. Maybe that's because we started the program in the debugger. So we can try something else. Let's start the program in debugging mode and attach with the debugger later on when we're in error mode. Maybe we see something there. So this is just a command line to start in the debugger. So we just set agent lib, say we want to listen on port 8000, and we don't want to start in suspended mode, just run. Okay, so you see we're in error mode now. First, we got the first error in iteration 1, then no, first error iteration 10,001, then OK again, then error in iteration 20,000. Now we attach with GDB, and we set a breakpoint. Stop in atomic long test. It's the place where the comparison happens. So just let's see what GDB tells us. We stopped at a point. We want to know the value of atomic long test.l. So they are equal. We also want to see our counter. Atomic long. Should have chosen a shorter class name. Maybe next time when you invite me one more time. Okay, and then we say continue, because I mean everything seems okay. And just let's see. And indeed, I mean we've been in error state. Here I can press this, it's no problem, it's not in a GDB. So we were in error state, and then we attached with the debugger, we actually attached at this iteration, which you can see here when I printed the count value, it was this one. And yeah, the values were equal, right? And yeah, they were really equal. Okay. Then I say continue. I disable the breakpoint. It's still okay. How do I disable the breakpoint? I think. Clear, thank you. Clear. Test.
Not slow, not long, but long.
It's not GDB. So you see, once we clear the breakpoint, we again get an error. So maybe most of you have already realized that this has to be related with JIT compilation. So you know, with Java debugger, you cannot really debug generated code. Once you attach with the Java debugger, the code gets de-optimized and you're again in interpreted mode. So this is an error of the compiler. So you have no chance to find it with the Java debugger. So that's actually my point I wanted to make. Sometimes you really need to do native debugging, even if it looks like strange or complicated, but sometimes you have no option, especially if you're developing Java VM. So then let's start with the real debugger, right? So we go into GDB. We put a breakpoint in our breakpoint helper function, which you remember from the template interpreter example. It also works for the compiler. So we set a breakpoint in breakpoint, and then we say we run the program and we use the -XX option compile command. Compile command. Compile, okay. And with this option, we can pass specific options to the JIT compiler. And we say him that we want to break at atomic long test update. And yeah, we run the program, atomic long test, and we run it 20,000 times. So now the JIT compiler, what he will do is, when he will start to compile our method, the atomic long test update, he will call this breakpoint callback. When you have a look at where we are actually, you see we are in the compiler thread. So this here compiler broker, C2 compile method, compile, print compile message. Actually, at the starting of the compilation of our method, it now called the breakpoint. But we are not interested in how the method gets compiled. We are interested to stop when it's first called the first time. So we just continue. The second breakpoint, it's again when the compiler starts the optimization step. So these are various scenarios which you may want to stop at. You may want to stop at the compilation, you want to stop during optimization of a method, or you may want to stop when it's first called. And that's the last, that's the stop where we're interested in. And this actually this one. So when we say where, again you see that the GDB has no idea where we are. It just knows that we're in our breakpoint helper function, but it doesn't know the other frames. So we will use our pre-native stack trace function to make sure that we are really in our update function. So we give him the, we have to step up, right? Because we're in, but for the stack trace that's no difference. So we call our mixed stack trace with the stack pointer, the frame pointer, and the PC. And you actually see we are in the atomic long test update method, right? And it says it's C2 compiled, and it's an uppercase J, which means it's a compiled method. So if I wouldn't have turned up tier compilation, you also would see here, you could see frames which have C1 or C2. Yeah, and that is actually the main method, and then which is still interpreted, because you remember I've turned off on-stack replacement. So on-stack replacement is a feature like when the VM notices that we are in a very long loop, then it de-optimizes an interpreted frame, compiles it, and calls it again in compiled mode, because usually you just compile methods which you call, and to don't get caught in the long running interpreted loop, you have this feature like on-stack replacement. But they switch it off. That's why the main method doesn't get compiled, but the update method gets compiled. Okay. So now we go up the frame to get right into our compiled update method, yes? And again, we use the find method, which is inside our hotspot, a helper method. And you see actually hotspot knows this address, and it knows that this PC, this belongs to an n method. N method is the name of the compiled methods in the hotspot. It's just a class, n method. And it's actually a compiled method, C2 compiled, for the Java update method. And it has various information, how much memory it uses in the heap, and where it has the oops and metadata. It's not interesting for our current topic here. But what we are interested in is in the actual code which got generated, because obviously it must be wrong, right? So let's look at the assembly. And I will now try to explain that a little bit, but maybe easier to do that here on the slide, because I have commented the code here already. Maybe you see it better, but it's actually this one here. So it's actually the same code you saw before, but I have just commented the line to make it more easier. So what we first do is we load the atomic long test class, then with the offset A0 from the class, we load the AL, the atomic long object. You remember AL was a static member of the class. So it belongs to the class. It's stored in the class object itself. Then we move the constant. So this is our 4 billion. It's the constant we want to add to both, to L and AL. We move it to the R8 register. We add the constant to offset actually to L, which is it's a member of the atomic long class at B0, or offset B0, there's the long variable. This is a null check for the AL object which we load before. So L is just a primitive type, so it doesn't have to check anything. But AL, it's an object, so it could actually be 0. So we have to do a 0 check, a null check. Otherwise, we may get corrupted code. And then here's actually the add, which adds the constant to our AL value object. And you see, it's 0. So actually, you would expect it would be the same, like the constant we are adding to our long value. But for some reason, when we add the constant to the atomic long object, it's 0. So now the task is to find out why it's 0. Yeah, I can just show you that what I've showed you and told you before on the slide, that this is really the class object. Call, find, just use this address, and actually the hotspot knows that this is our class object, and it tells us which methods the class contains. This is the class name, atomic long test, and here below you can also see somewhere we can also see, yeah, actually here you can see the various offsets. So here is the offset of the L of the long variable, and there's also the offset of the AL object, that what was used before. So let's now step until the actual point where it happens, right? We want to step until we set a temporary breakpoint here, where we compare the two values, and we print the two registers, R11 and R8, and they are not the same, right? When we continue, yeah, we actually now continued, and you see we got this error. So these values which we printed before, and actually they arrived now in Java land, and our update method printed the error. This is the output of our Java program, and it was the 1001st iteration. So the first time the JIT generated code gets executed, we get this error. Then the next iteration, it's good again. So this is because I will explain you that later. I think we're running out of time. I just show you how to fix this problem. Then while we are rebuilding the VM, I will explain you why we get just one error. So in order to see, we have now seen the assembly of the generated code, but you have no idea why Hotspot made this error. So there is another nice option, and it's called print opto-assembly and print assembly, which gives the opto-assembly is like the Hotspot's view of the code it wants to generate. And if you run it, -xx print opto assembly -xx compile command equals. Now we don't want to stop at the method anymore because we know that it's wrong. We want to say that we want to print the assembly atomic long test dot update atomic long test. Yes, we started from the beginning. Again, print Oh, I forgot the plus, sorry. So now this is, we are looking for atomic long. So this is actually the opto assembly of our atomic long update function, and you see it's like commented. It's the different blocks. You see B1, B2. That's actually the basic blocks generated by the HotSpot compiler from the Java bytecode. It just builds up a tree and builds basic blocks. And you see there is one place here where we have the this is the add. This is the add where we increment the long integer, and where is the yeah, sorry. This is here we increment our long constant, but first we have loaded the. First, we load the constant into our 8 register, which you saw, and then we increment the long value. But for the increment of the object, we use this addq instruction with this constant. And if you know x86 assembly, you may know that the addq command, it has the constant in the instruction, and it has only 32-bit for the constant. But this is more than 32-bit. So actually, it's you saw it before. It's 1 and 32 zeros. So the addq command is not capable of adding such a constant. It will just wrap it around and just use 0. So this is the opto assembly, and it's actually what gets generated. What you generate is an add with 0, what we saw in the code. And now, how can we fix this? What we can do is we can just look at the source code of the hotspot and grab for add to see where that happens. And it happens that add, it's the so-called AD file, which is the architecture description of the hotspot. So actually the C2 compiler, it's in some sense similar to the template interpreter in that it generates a graph of your Java method. But in the end, it's first an ideal graph, which gets optimized with various methods. But in the end, it's converted into a machine graph, where finally for each node in this graph, you have to actually generate some machine code. Somewhere you have to end, right? And there are, for every logical node in this graph, there is a small code snippet in the ID file, which contains code, which contains the actual machine instructions for this node. And one node is this addq node. And if we open it in Emacs, we go to this addq node, and we see that it actually it generates code here, addq, with this constant. And this constant, it's an immediate long. So this is not actually C. This is just an internal language used in the hotspot to generate this code. And it's actually an immediate long, which I say it's 64-bit data type. So if we would change that into 32-bit, I think it's just like this. And then rebuild the whole VM. It will take about 1 minute, in which I will take some questions because we are also out of time. And then we will just run the new hotspot, and hopefully it will have no more errors. So yeah, that's the end of my talk. Please, if you have any questions, I mean, we're also out of time, but I think there is only lunch now, so if you want to have some question, I can still answer them. So thanks for listening.